When installing a ground fault circuit interrupter or GFCI breaker and a neutral conductor is not available, there are several important steps to follow. Firstly, it is critical to not connect a neutral conductor to the circuit board for the motor. This action can lead to damage to the motor or create a potential safety hazard. Now let's discuss how to install a GFCI breaker without a neutral conductor. 1. Always check local building codes. Some jurisdictions may have specific regulations regarding the installation of GFCI breakers without a neutral conductor. It's essential to ensure compliance with these local requirements to avoid any code violations and ensure safety. 2. Use a non-neutral dependent GFCI breaker. These breakers are specifically designed to sense current imbalances only on the hot and cold conductors. They are intended for applications where a neutral conductor is not accessible, such as swimming pools and spas. Standard GFCI breakers require a neutral connection to function correctly, so it's crucial to use the appropriate type. 3. Connect the line, which is the hot, and load, which is also the hot, wires to the designated breaker terminals. Make sure that you do not connect a neutral wire to the breaker, as it is not needed for this specific type of GFCI breaker. 4. Install the breaker in the load center. Ensure that all screws are securely tightened to provide a reliable electrical connection. Loose connections can cause overheating and potential hazards. 5. Test the GFCI breaker after installation. Press the test button on the breaker to verify that it is functioning correctly. The breaker should trip, indicating that it is detecting a simulated ground fault. If the breaker does not trip, there may be an issue with the wiring or the breaker itself, and further investigation is required. Additional notes to consider are that non-neutral dependent GFCI breakers are typically more expensive than standard GFCI breakers. This is due to the more complex circuitry required to detect ground faults without a neutral connection. Also, the load center must be properly grounded to ensure that the GFCI breaker functions correctly. Grounding provides a path for fault current to flow, allowing the GFCI breaker to detect imbalances and trip. Finally, it is always recommended to consult a licensed electrician if you are not familiar with the electrical wiring or have any doubts about the installation process. Electrical work can be dangerous, and a qualified electrician can ensure that the installation is done safely and in compliance with all applicable codes and regulations. Regarding the 2017 National Electrical Code, or NEC, there are several relevant sections that pertain to GFCI protection. Article 210.8 covers ground fault circuit interrupter protection for personnel. This section specifies where GFCI protection is required in dwelling units and other locations. In dwelling units, GFCI protection is required for receptacles installed in bathrooms, garages, outdoors, crawl spaces, unfinished basements, kitchens, and laundry areas. For other than dwelling units, GFCI protection is required in bathrooms, kitchens, rooftops, and outdoors. Article 680 covers swimming pools, fountains, and similar installations. This article has extensive requirements for GFCI protection, bonding, and grounding to ensure safety in and around these locations. Section 680.22 specifically addresses GFCI protection for receptacles near swimming pools and spas. Receptacles that supply power to pool pump motors must also have GFCI protection. Section 680.26 outlines the requirements for bonding metal parts of the pool or spa structure to create an equipotential bonding grid. This helps to minimize voltage gradients in the pool area and reduce the risk of electric shock. Section 680.42 covers the wiring methods for swimming pools and spas. Wiring must be installed in conduit or other approved raceways to protect it from physical damage and moisture. Article 682 addresses natural and artificially made bodies of water. GFCI protection is required for electrical equipment installed within a certain distance of these bodies of water. Section 682.15 specifies the requirements for GFCI protection for marinas and boatyards. Receptacles used to supply power to boats must have GFCI protection. Article 547 covers agricultural buildings. GFCI protection is required for receptacles in certain agricultural buildings such as those used for livestock confinement. Section 547.9 outlines the requirements for GFCI protection in agricultural buildings. Article 550 covers mobile homes, manufactured homes, and mobile home parks. GFCI protection is required for receptacles in mobile homes and manufactured homes. Section 550.13 specifies the requirements for GFCI protection in these types of dwellings. It's important to note that these are just a few examples of the many NEC sections that pertain to GFCI protection. The specific requirements may vary depending on the application and location. Always consult the latest edition of the NEC and local codes to ensure compliance. Let's delve deeper into the technical aspects of non-neutral dependent GFCI breakers. These breakers operate on the principle of differential current sensing. A standard GFCI breaker monitors the current flowing through the hot and neutral conductors. In a normal circuit, the current flowing into the device through the hot conductor should be equal to the current flowing back out through the neutral conductor. If there is a difference of 5 mA or more, the GFCI breaker trips, cutting off power to the circuit. Non-neutral dependent GFCI breakers, on the other hand, only monitor the current flowing through the hot conductor. They use a sensing coil that detects any imbalance between the current flowing into the device and the current returning through the grounding conductor. If there is a ground fault, a portion of the current will flow through the grounding conductor instead of returning through the hot conductor. This imbalance is detected by the sensing coil, which triggers the breaker to trip. The internal circuitry of a non-neutral dependent GFCI breaker is more complex than that of a standard GFCI breaker. It requires additional components to accurately sense the current imbalance and differentiate it from normal circuit fluctuations. These breakers typically use a solid-state electronic circuit to process the signal from the sensing coil and activate the tripping mechanism. When installing a non-neutral dependent GFCI breaker, it is crucial to ensure that the grounding system is properly installed and connected. The grounding conductor provides the path for fault current to flow back to the source, allowing the GFCI breaker to detect the imbalance and trip. If the grounding system is not properly installed, the GFCI breaker may not function correctly, and the risk of electric shock will increase. Some common causes of nuisance tripping in GFCI breakers include faulty appliances, loose wiring connections, and moisture. Faulty appliances can leak small amounts of current to ground, which can trigger the GFCI breaker. Loose wiring connections can create intermittent ground faults, causing the breaker to trip randomly. Moisture can also create a path for current to flow to ground, especially in outdoor or damp locations. To troubleshoot nuisance tripping, first, disconnect all appliances from the circuits and reset the GFCI breaker. Then plug in each appliance one at a time to see if any of them cause the breaker to trip. If you find a faulty appliance, have it repaired or replaced. Next, check all wiring connections to ensure that they are tight and secure. Look for any signs of damage or corrosion. If you find any loose or damaged connections, repair or replace them. Finally, try to keep the area around the GFCI breaker dry and free from moisture. If the problem persists, consult a qualified electrician to diagnose and repair the problem. When selecting a GFCI breaker, it is important to choose one that is rated for the appropriate voltage and current. The voltage rating of the breaker must match the voltage of the circuit. The current rating of the breaker must be equal to or greater than the maximum current that the circuit is expected to carry. It is also important to choose a GFCI breaker that is listed by a recognized testing laboratory, such as Underwriters Laboratories or UL. UL listing indicates that the breaker has been tested and meets safety standards. GFCI breakers are available in different trip current ratings. The most common trip current rating is 5 mA, which is the level at which the breaker is required to trip to protect personnel from electric shock. GFCI breakers are also available with trip current ratings of 30 mA, which are used for equipment protection. These breakers are designed to protect equipment from damage due to ground faults, but they may not provide the same level of protection for personnel. In addition to GFCI breakers, ground fault circuit interrupter receptacles are also available. GFCI receptacles provide the same level of protection as GFCI breakers, but they are installed at the point of use instead of in the load center. GFCI receptacles are commonly used in bathrooms, kitchens, and other locations where there is a high risk of electric shock. When replacing a standard receptacle with a GFCI receptacle, it is important to follow the manufacturer's instructions carefully. The GFCI receptacle must be properly wired to function correctly. It is also important to test the GFCI receptacle after installation to ensure that it is working properly. In summary, GFCI protection is an essential safety measure that helps to prevent electric shock. GFCI breakers and receptacles are designed to detect ground faults and quickly cut off power to the circuit, reducing the risk of injury or death. When installing or working with GFCI devices, it is important to follow all applicable codes and regulations and to consult a qualified electrician if you have any questions or concerns. Proper grounding techniques are crucial for the effective operation of GFCI protection. The grounding system provides a low impedance path for fault current to flow back to the source, allowing the GFCI device to detect the imbalance and trip. There are several different types of grounding systems, including the grounded system, the ungrounded system, and the impedance grounded system. The grounded system is the most common type of grounding system. In a grounded system, one of the circuit conductors is intentionally connected to ground. This conductor is typically the neutral conductor, but it can also be a phase conductor in some cases. The grounded system provides a low impedance path for fault current to flow back to the source, allowing the GFCI device to detect the imbalance and trip. The ungrounded system does not have any intentional connection to ground. In an ungrounded system, a ground fault will not cause a large fault current to flow. Instead, the voltage of the ungrounded conductors will rise to the line to ground voltage. This can create a dangerous situation, as the insulation on the conductors may not be able to withstand the increased voltage. The impedance grounded system uses an impedance such as a resistor to limit the amount of fault current that can flow to ground. This type of system is typically used in industrial applications where it is important to limit the amount of fault current to prevent damage to equipment. The NEC specifies the requirements for grounding electrical systems. Article 250 covers the general requirements for grounding and bonding. This article includes requirements for grounding electrodes, grounding conductors, and equipment grounding. Section 250.4 outlines the general requirements for grounding electrical systems. Section 250.24 covers the requirements for grounding separately derived systems. Section 250.30 covers the requirements for grounding electrode systems. Section 250.118 lists the acceptable types of equipment grounding conductors. Bonding is the process of connecting all metal parts of an electrical system together to create an equipotential plane. This helps to minimize voltage gradients in the event of a ground fault and reduce the risk of electric shock. The NEC also specifies the requirements for bonding electrical systems. Section 250.92 covers the requirements for bonding service equipment. Section 250.96 covers the requirements for bonding metal water piping systems. Section 250.104 covers the requirements for bonding other metal parts. In addition to the NEC requirements, there may be local codes and regulations that govern grounding and bonding. It is important to check with the local authority having jurisdiction to ensure compliance with all applicable codes and regulations. Proper grounding and bonding are essential for the safe and reliable operation of electrical systems. By following the NEC requirements and local codes, you can help to protect people and equipment from electric shock and other electrical hazards. Let's explore the application of GFCI protection in specific scenarios such as hot tubs and spas. Hot tubs and spas are considered high-risk areas for electric shock due to the presence of water and the potential for electrical equipment to come into contact with water. As a result, the NEC has stringent requirements for GFCI protection in these locations. Section 680.42 of the NEC specifically addresses the requirements for GFCI protection for hot tubs and spas. This section requires that all 120 volts and 240 volts receptacles located within 10 feet of the inside wall of a hot tub or spa must be GFCI protected. This includes receptacles that supply power to the hot tub or spa equipment, as well as any other receptacles that may be used by occupants. In addition to receptacles, the NEC also requires GFCI protection for other electrical equipment associated with hot tubs and spas. This includes lighting fixtures, pumps, heaters, and any other electrical devices that are installed within 5 feet of the inside wall of the hot tub or spa. The GFCI protection must be provided by a GFCI breaker or a GFCI receptacle. It is important to choose the appropriate type of GFCI device for the application. GFCI breakers are typically used to protect entire circuits, while GFCI receptacles are used to protect individual outlets. When installing GFCI protection for a hot tub or spa, it is important to follow the manufacturer's instructions carefully. The GFCI device must be properly wired and grounded to function correctly. It is also important to test the GFCI device after installation to ensure that it is working properly. In addition to GFCI protection, the NEC also has requirements for bonding and grounding hot tubs and spas. Bonding is the process of connecting all metal parts of the hot tub or spa together to create an equipotential plane. This helps to minimize voltage gradients in the event of a ground fault and reduce the risk of electric shock. Grounding is the process of connecting the hot tub or spa to the earth, providing a path for fault current to flow back to the source. The NEC requires that all metal parts of a hot tub or spa, including the metal shell, the metal frame, and any metal piping, must be bonded together. The bonding must be accomplished using a solid copper conductor that is at least number 8 American wire gauge, or AUG, in size. The bonding conductor must be connected to a bonding terminal on the equipment grounding conductor. The NEC also requires that hot tubs and spas be grounded to the equipment grounding conductor. The equipment grounding conductor must be sized according to the overcurrent protection device for the circuit. The equipment grounding conductor must be connected to the grounding electrode system for the building. The grounding electrode system typically consists of a ground rod, a metal water pipe, or a concrete encased electrode. It is important to note that the NEC requirements for GFCI protection, bonding, and grounding hot tubs and spas are complex and can be difficult to understand. If you are not familiar with electrical wiring, it is best to consult a qualified electrician to install or repair electrical equipment for a hot tub or spa. Failure to comply with the NEC requirements can result in serious injury or death. Always prioritize safety when working with electricity, especially in wet environments such as hot tubs and spas. Consulting with a licensed electrician ensures that the installation meets all safety standards and local code requirements.